This is the first lecture of Chapter 2 of our textbook, which is titled Atoms, Molecules, and Ions. Chapter 1 introduced us to the scientific pursuit and to some of the fundamental arithmetic that you will be expected to demonstrate for the rest of the course. So Chapter 2 kind of builds off of that foundation, only now we're going to be pivoting to focus specifically on chemistry. So like all studies, chemistry has its own vocabulary, and that vocabulary is naming chemical compounds. So that's going to be a very critical skill for you to develop proficiency in by the end of this chapter. Because moving forward, everything that we're going to be talking about will involve a chemical reaction, and chemical compounds are the building blocks of those chemical reactions. So it's important that you're able to look at a chemical formula and name it, or vice versa, in order to navigate this class and to know what the heck we're even talking about. So my expectation is that you've already watched the videos that go over sections 2.1 through 2.4 of this chapter, which focuses on the history of atomic theory up through Rutherford's discovery of the nature of the nucleus. I'm not going to review any of that material, but it is something that you're expected to know. So do read those sections in your textbook and at a very minimum, watch those videos. They're entertaining. They do a better job than I would do. And they have cool animations, which I have neither the time nor the skill to make. So chapter 2 is super important, so let's get moving. So here we have a figure of basically a simple atom. This would be helium, and this is showing us the current model of how we think atoms are put together, which after watching that first video, you know, is a pretty good, got some pretty good data to back up our theories. So here, orbiting our nucleus is going to be our electrons. Our positively charged particles, which are equal and opposite in charge to those electrons, are our protons. And these neutral particles here are our neutrons. This structure here is called our nucleus. And the nucleus is going to be responsible for the vast majority of the mass of our atom. So the nucleus is very dense, and it contributes most of the atom's mass. In contrast, electrons, the only subatomic particle that's not part of the nucleus, electrons are going to be orbiting that nucleus. They are very light. They have very small mass relative to a proton. And they are going to be the particle that engages in chemical bonding. So you can imagine, after hearing that description of an electron, that this class is going to be very focused on electrons. Why? Because chemical bonds make molecules, and the breaking and reforming of chemical bonds are the definition of a chemical reaction. So chapter 7 and 8 of our textbook is really focused just on electrons and electron behavior. So we have 2 whole chapters to explore that. In this chapter, we're just going to develop kind of a working knowledge of electrons, and we can analyze chemical reactions just with that working knowledge, and then we'll really deep dive in chapter 7 and 8. So much more fun is to come, let me tell you. Okay, so just kind of some of that same information, but just written a lot more nicely than my handwriting. we have our nucleus, protons and neutrons, electrons negatively charged. Remember, protons and electrons are equal and opposite in charge, but they have very different masses. Protons are much heavier than electrons. I like this figure from your textbook because it does a good job of showing the relative size of the nucleus to an atom. So most of an atom is actually empty space, which is kind of one of those like mind-blowing moments, like that Neil deGrasse Tyson quote from lecture 1, where you realize that everything around you at the atomic level is mostly empty space, which means because atoms make up compounds, compounds make up literally everything around you. Everything around you is mostly empty space. That's cool, huh? I like it. Okay, so a couple things we want to get down here. We understand the charges. Neutrons, I think, get glossed over a lot, and they're really important, and we're going to talk about them in the next few slides. So I just want to talk a little bit about what they do. So if we were to go back one slide, actually, you can see here that we have our protons all kind of nestled together with our neutrons. So remember, protons are positively charged. That's why they have this like positive symbol on them here. So we know, just from existing for as long as we have, that like charges repel and opposite charges attract. And we know that this is our nucleus and that it's super, super dense, right? So you have positively charged particles that are in really close proximity to each other. That should be your first like, how is that possible? Why aren't they just repelling each other? And the reason why is the neutrons. So neutrons are going to stabilize the nucleus by minimizing charge repulsion. Okay, so they're really critical as stabilizing factors. Okay, so that's the function of neutrons in the nucleus. So now let's get a couple other critical concepts down. That is that protons are going to be the defining characteristic of an atom. Why are they the defining characteristic? Because if you have a nitrogen atom, it has 7 protons. If it has 8 protons, it is not nitrogen. If it has 6 protons, it is not nitrogen. Protons define an atom. In contrast, neutrons and electrons can both be variable in an atom. So you can have a nitrogen with a couple different configurations where there's different neutrons, and those are called isotope. So isotopes are going to be a variable number of neutrons in an atom. Likewise, electrons can be different, and those are called ions, which is a variable number of electrons in an atom. All right, we're going to talk about each one of those conditions in a second, so we'll have plenty of time to develop some familiarity. All right, look at that, 1 second. So isotopes, again, variable number of neutrons. So here we have a sodium, and the sodium has 11 protons. And if you look at your periodic table, which you should always have in front of you when you're watching these lectures, and you find sodium, which is in that first column of the periodic table, it has the symbol Na, and right above that is a number 11. That number is its atomic number, and that matches the number of protons. So if you look at carbon, that atomic number is 6. Carbon has 6 protons. You look at fluorine, that number is 9. Fluorine has 9 protons. Very cool. But as we see here, we have our sodium, atomic number 11, 11 protons, different number of neutrons. So in this case, we have 12 neutrons, and here we have 13 neutrons. So both of those can be completely stable isotopes that would have or could be relatively abundant in nature depending on the particular element. And if you notice here, this is kind of the symbol that we're going to learn about and that we'll use to describe a particular atom. Here we have our atomic number, which matches the number on the periodic table for that particular element. And here we have a mass number. And that mass number is going to be the number of protons plus neutrons. So you can think of that, because we know that that the vast majority of an atom's mass comes from its nucleus, it makes sense that the mass number would just be looking at the protons and neutrons. Okay, so you can have stable isotopes and you can have unstable isotopes. And scientists, because they're clever, have developed a way of utilizing unstable isotopes for medicinal purposes. So you may have heard of radioactive labeling, or have known someone who went in for a test where they injected the person with a radioactive dye. Now, that's radioactive dye. So here's a couple examples where we have cobalt-60. That can be used in radiation therapy to prevent cancer. There's a lot of different examples here. So carbon-14 is used to study metabolism. You might already be familiar with carbon-14 if you've heard about carbon dating. So we've talked about isotopes, but why are some isotopes radioactive? Radioactive isotopes are going to be isotopes that are not as stable. So they're not going to be very commonly found. We call that abundance, right? They're not going to be very abundant in nature. And because they're unstable, this really cool phenomenon happens where the nucleus will spontaneously rearrange in order to make the nucleus more stable. In doing so, it throws out or emits particles, and those particles can be measured with instrumentation. So that process of emitting particles from a nucleus as it's rearranging to form a more stable state is called radioactive decay. Very cool. Like I said, carbon-14 is also used for carbon dating. So carbon-14 is relatively stable and it takes a long time to decay. It's also present in all organic matter. So if you have something and you're interested in its age, like you would be if you were an archaeologist or a forensic scientist, you could use the abundance or the amount of carbon-14 in that sample to deduce how old it is, which is really cool, right? Scientists are clever. Okay, so this is a really cool figure that I found. I'm just going to blow it up so we can actually see it here, or so I can see it. So these pie charts here are just representing the relative abundance of the isotopes of that particular element. So if you look at gold, we can see that really gold is only going to have one form. And all of these elements that are in blue here fall into that category. So that's pretty cool. Then you have in yellow and pink elements that have multiple isotopes. You don't need to memorize this. I just think it's a really cool figure because it's very interesting and relevant to atomic mass, which we're going to talk about in chapter 3. So just having this awareness now is going to help us in chapter 3 understand the molar mass of a species. So you can see carbon, we have carbon 12 is much, much more abundant than carbon 13. Those are the two stable forms of carbon isotopes. And that is going to be relevant when we talk about atomic mass, which I won't get into now because that is not one of the subjects of chapter 2, right? Stick to your role or your lines. Yeah, but this is a cool figure. I like it. Okay. So isotopes can be different. That's going to affect the mass number, which reflects the number of protons and neutrons of an individual atom of an element, right? So ions are going to be atoms with a variable number of electrons. And what we're going to see is that ions form in a pattern reflected, thank goodness, on the periodic table. We're going to get there, so you don't even have to write that down. I'm just writing it down for emphasis. Okay, so here we have sodium, and we're just looking now at the charged particles of a particular atom. So sodium, 11 protons, right? Its atomic number is 11 on your periodic table right here. So if it has 11 protons and 11 electrons, this would be a neutral sodium, which would be its form as like a stable atom, right? Now, sodium, and we'll find out why in a couple slides, can also be found with one fewer electron. And so it is going to be a sodium ion with a positive charge. So remember, electrons are negative, which means if you lose an electron, you are going to become positive. Right? That might sound really simple, but it's something that's really easy to lose sight of, right? Lose an electron, become more positive. So that is why we have Na+, because it's lost an electron. In contrast, chlorine, if it has an equal number of electrons and protons, is a neutral atom. If it has gained an electron, then it would have 17 protons, 18 electrons. Again, electrons are negatively charged particles, so if you gain an electron, that means that you are going to become negative. Okay, so this doesn't just spontaneously happen. What you're going to have instead is a species like sodium, which can lose an electron, a species like chlorine, which can gain an electron, and they're going to be in the same environment, under the right conditions, and we will actually have this single electron from sodium from its outermost shell, right? There's more electrons here that sodium possesses. They're just not being shown because they're not engaged in bonding. So that electron can be pulled from the sodium to the chlorine for reasons that we'll talk about when we talk about ionic bonds. And as a result, you have a positively charged sodium ion and a negatively charged chlorine ion. And you can see this electron is in purple, representing that it was donated by sodium. Right? Positive ion, negative ion. We're going to find out that there's a name for each of those in a moment. Okay, so we just talked about a lot of different ways that a atom can have some variability with it, right? Protons are not going to be varied, but you can have a different number of neutrons forming an isotope, or you can have a different number of electrons forming an ion. So it's important for us to have a way of representing a single atom and letting our audience know what its composition is. So how many neutrons does it have? How many electrons does it have? And the way that we do that is via atomic symbols. So an atomic symbol, X here is just representing what the element symbol is. So our example here would be our sodium. Z is that atomic number. So remember, we've already talked about atomic number. This is going to be the number on your periodic table. And it equals the number of protons. So one fun fact is that because we already have the element symbol, the atomic number is kind of redundant, right? You can't have sodium unless it has 11 protons. So you will see in, especially scientific papers or in actually even in our textbook in future chapters, this will sometimes be omitted, but we are not going to omit it because it is part of this atomic symbol. So atomic number is your number of protons. Mass number, we've already talked about, that's the total number of protons and neutrons. You can think of that as reflecting the mass of the nucleus, right? Or the composition of the nucleus. So this is your number of protons plus neutrons. And what we're going to see is that you can also have a piece of information here if it's an ion, which is going to be the ion charge. Right, and what that would look like would be either a positive symbol or you could have a negative symbol, and we'll do some examples right now. Yeah, do it. Okay, let me change our color, because right now, for whatever reason, I'm very pink. Okay, so let's practice some atomic symbols. So I'm just going to get that information that we just lost back up here. Z is our number of protons. A is going to be the protons plus neutrons. And then we also can have, and I'm going to put this in like, it's going to be the charge. And charge can always be found by taking your protons minus your number of electrons. If you always do it, protons minus your number of electrons, then you will always have the correct sign, which is really nice, protons minus electrons. Okay, so let's say that we have an atom, and we know that for protons, it has 26, electrons is 22, and neutrons is going to be 25. So we want to write the atomic symbol for this. This is very similar to problems that you're going to see in your recitation packet, so we'll just do a couple. So the very first thing that you want to look at is your protons. Why? Because this is going to tell me what species I'm working with. So if it's 26, I need to find number 26 on our periodic table, and you'll see that that is iron. Right, and then to be redundant, we just go ahead and write that for Z, which is our atomic number. All right, atomic mass is going to be our number of protons plus electrons, so 26 plus 25 is 51. And for our electrons, it has here that there's 22 electrons. So our number of electrons is different than our number of protons, so we know it's going to have a charge. We can see that we have more protons than electrons, which means that we have more positively charged particles than negatively charged particles. So we know that this is going to be a positive ion. The difference between protons and electrons, 26 minus 22 is 4. And so the way that we write this is 4 positive. So you always write the charge of the ion before its symbol of positive or negative. That becomes significant in chapter 4. For now, just think of it as like, well, this is just the way it's done, and we're working with what we inherited. Okay, let's just do one more example. I'm just going to use an abbreviation for protons, neutrons, and electrons. So let's say we have protons are 17, our mass number, otherwise known as A, right, up here, A, is going to be 26, and our number of electrons is 18. I said I was going to use abbreviations. We usually just use PN and then the E with a negative symbol. This you're going to become really familiar with. I'll basically never write electrons again in this class because I don't have to. It's great. Ever read a scientific paper? We use an abbreviation and then we just expect you to remember what it was, right? Because we don't have time. We don't have time to write electrons, but we do have time to explain this. Okay, so I see that my protons and my electrons are different. And I have more electrons than protons. I have exactly one more. So I don't know what this species is, but I do know that it's going to be negative. My mass number is 26, so that would go up in this corner. And so now I need to figure out what my number of protons is. Well, we can use this, P plus N equals A, in order to figure out what our number of protons is. So if P plus N equals A, then we know that our number of protons is going to be A minus N. So our number of protons equals A, which is 26, minus our number of neutrons. Hold on one second. That's not what I meant to do. Never mind. You couldn't solve it this way because I haven't told you the number of neutrons. And but it's a charge of -1, 26. That means we have, we have 17 protons there. You know, sometimes you just get ahead of yourself. Okay, we have protons. We don't need to do any of the stuff that we just looked at, that I just did. But look, right? That is a useful skill if you needed it, which you don't need right now. Let's just forget that happened, huh? Right? If one was better at or cared more, no, it's not that I don't care. It's that it would take too much time to splice this all together, and I can't stand the sound of my own voice. So, you know, we're moving on. Okay, so we know that this is negative. Oops. We know that it's a negative charge. I didn't have to erase all of it. This is 26. Our number of protons is given to us right there. Right there. Yep. 17. So all we have to do is find 17, and that would be chlorine. I thought that I had made this harder, but actually it's just very similar to the one before. That's okay. There you go. Okay, you get a ton of practice with that in the recitation packet. So let's move on. Okay. So definitely get some practice with those. Okay, so we're just going to cover a little bit more material before we get into naming, which is going to be the subject of our second lecture. So the periodic table gives you a lot of information. It is so much information that by the end of this class, your periodic table, which started out as this like very clean piece of paper, should have a ton of information written on it. That's something I really encourage my students to do, is to personalize your periodic table and then have it for every quiz, every exam, every lecture, because you need to develop really quite a bit of familiarity with the periodic table. And that familiarity and understanding of the way that it's put together and the significance of the periodic table is only going to grow as we work through this class. So this is a nice figure for us that divides the periodic table according to the different sections. So one of the most important things, let me pick a color that you'll be able to see, to recognize is that we have this kind of like staircase of the periodic table, which is right here. And that staircase is going to separate our nonmetals from our metals. So everything that is to the right of my staircase is a metal. Everything to the left of my staircase is a nonmetal. And we're going to see in a minute that that's really important. There's one exception to this rule, because there is always one exception, and that is hydrogen. So hydrogen is located on the left-hand side of the periodic table because of some of its bonding trends, which we're going to talk about. Yeah, we'll talk about it in our second lecture. We won't get to it today. But you can think of hydrogen actually as existing basically like right here. Some periodic tables actually have hydrogen weirdly floating right there. Ours does not, and I'm okay with that. Okay, so we're going to actually go to a little bit simpler of a periodic table that shows you the terms that you will be expected to know. So first of all, the periodic table is divided into rows and columns, as you can see. The rows of the periodic table are called periods. The period number, or the row number that it's in, is going to be reflecting the complexity or the size of that particular atom. So as you're working down the periodic table, you're getting more and more protons, which means there's more and more electrons, more and more neutrons, more complex atom. So periods are our rows. Our columns are called groups. So what's really significant about groups, and something that you need to know, and by the end of this class you will have a very deep appreciation for, is that groups, actually let me let that go away for a second. I want to change this to elements in the same group, right? Group meaning column, have similar chemical behavior. So what does that mean, chemical behavior? We can think of that as like bonding trends. They're going to have some other similarities, but for now let's just think of it as like just chemical similarities, physical properties and bonding trends. Okay, so the first row of the periodic table are called alkali metals. Second row are called alkali earth metals. Then this period of this section of the periodic table is called the transition metals. And what you'll often hear me calling it is the valley of the periodic table, right? So if you step into the valley of the periodic table, you're talking about transition metals. You'll see that there are these species here that aren't quite in the valley, but they're like as you go back up. Aluminum, tin, as an example. Then we have our halogens, which are group 7A. So these are halogens in a compound. They're called halides. Totally cool. You'll hear me call them halogens or halides because we're usually talking about them in a chemical bond or a chemical compound, right? And group 8A, we have the noble gases. So noble gases are really interesting, very stable species, and they don't really, they're not really involved in much chemical bonding. Okay, so in green here are all of our metals. In blue, we have our nonmetals, and then in gray here we have our metalloids. So if you think of that the staircase, the metalloids are kind of bordering either side, and they have kind of some properties that are similar to metals, some properties that are similar to nonmetals. We will mostly be focusing this entire class on what are called the representative elements, and those representative elements are going to be those alkali and alkaline earth metals and this section of our periodic table. So these are called representative elements. They have chemical behavior that has been well studied and is like quite predictable. So we'll by and large be mostly dealing with these elements in our explorations of chemistry, especially as we move in towards quantum chemistry at the end of the semester. But I just want to draw your attention here where we have 1A, 2A, 3A, 4A. This is a way of naming our groups that is very common, and it is not on the periodic table supplied to you in this class. I would recommend that you add it. I would recommend color coding it similarly to this and naming the different groups. Again, make it your own, make it something that's useful. Also know that you're going to be adding a lot of stuff to it. So maybe pencil, I don't know. Live your life. Throw caution to the wind. Okay, so this is our second to the last slide. So we have atoms, elements, and compounds, and these are all things that we're discussing in this chapter. So atom and elements are kind of used interchangeably. What's important is an atom is just going to be talking about one single thing, right? Single entity, so a single helium, for instance, or we were just talking about single sodiums, right, when we were making that atomic symbol. We can also have an element that is in a molecular form, like oxygen is found, and that is still an element because it is a pure substance, right? It's only oxygen atoms. So then we have compounds. Compounds are mixtures of atoms that have come together to form a compound. So in this case, we have water. You have two hydrogens. Oh, that's misspelled. I didn't make it, right? These people did. But I just noticed, and I've used this for like 3 semesters. That's fun. So that's 2 hydrogen atoms and 1 oxygen atom. So I do just want to really quickly talk about oxygen here. So there are a couple different elements that we find in their molecular form, like oxygen is here. And those are called homonuclear or diatomic molecules, right? The prefix homo meaning same, nuclear, nucleus, right? Specifically looking at the number of protons. Diatomic meaning 2 atoms that have formed a molecule. So examples are the ones that we're going to encounter all the time in this class is oxygen, nitrogen, and then group 7A. So that's going to be fluorine, chlorine, bromine, and iodine. And hydrogen. So often when you see in this class like a chemical reaction as we move forward to future chapters, and they say that oxygen is one of the species, they are talking about oxygen molecules. So oxygen is not stable as a single atom. It will always find another oxygen and form a molecule. So those are called homonuclear diatomic molecules. But this is a pure substance, so it's an element. Okay, compound, 2 different atoms that have come together. In this case, we have hydrogen and oxygen. Okay, so the rest of this chapter is going to be looking at molecules and bonding. So we have 3 different kind of bonds that we're going to talk about: covalent, ionic, and hydrogen bonds. You might already be familiar with those. We're going to explore each one individually. But I do just want to introduce you to this system in case you're not familiar. So in chemistry, we use subscripts and superscripts pretty commonly. So a subscript is when you have, like the example that we had when we in chapter 1, when we were exploring temperature, we had TC, right? Which meant temperature Celsius. This is a subscript. And subscripts are going to modify the preceding, I'm just going to say value. Right? In this case, that value would be temperature. Value, let's say, / variable. So when we look at a chemical formula, these subscripts are modifying the preceding element. So in one molecule of glucose, we have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So subscripts modify their preceding element. Okay, that's going to become important as we start to write chemical formulas, and we will leave that to the next lecture. Thanks.